Simulation neural network trained by two-dimensional finite difference time domain dataset for determining frequency responses of metagratings. I am Francis de la Cruz and this is our research. As you can see, this is Harry Potter with his invisible cloak making him invisible, and this works through magic. But the question is, can we make it in real life? And with the power of physics, actually we can do it right now. As you can see, there's a small device here that could actually cloak the fingers or even the hands of the experimenter. But this is a little bit limited. What if we want it more flexible? We want a real cloak. And that would involve really serious engineering on how we define the materials we have, like arranging this refractive index in a very bizarre way. This is what they call transformation electromagnetics. And if we want to make it real, to fabricate it, we might need the help of metamaterials. And these are materials that are really exotic compared to natural materials because when it interacts with light behaves differently. And we have also the 2D analog, which are metasurfaces. And these are working in the sub-wavelength regions where the elements are really small compared to the operating wavelength. And if we want to design these materials, we need to consider geometric parameters or the shapes and the material parameters. For example, permittivity, permeability, and conductivity. Also, we need to use the help of computational electromagnetics such as finite difference time domain method for us to know what will be the profile of these materials when exposed to light. And we could form various analyses and further improve our designs, like this one. And also, we can employ neural networks since neural networks can be used in a lot of ways. For example, classifying cats and dogs. And not only for classification, but for also facial recognition, image recognition, language processing, computer vision, and so on. So the question is, why we apply neural networks in this kind of field in optics, in frequency responses? Because designing metamaterials and metasurfaces involves a lot of configurations, lots of parameters, and neural networks will really make the simulation much faster. Take note that different shapes can result to different frequency responses even if they are made from the same materials. So using the images of the shapes could actually help us to identify the frequency response, whether using FDTD or the neural network. Also, why neural networks? In terms of times of simulation or doing calculation, your normal EM solvers could actually process from minutes to hours to even days for huge number of samples. But for your neural network, it would take you milliseconds to seconds. So the problem is, you can really use a neural network to determine frequency responses of electromagnetic devices trained using the dataset from an FDTD simulation. So, based from Moll et al., they actually have this study using your nano antennae or nanoplasmonic metasurfaces that could actually convert left circularly polarized wave to a right circular polarization wave. And then they look for the conversion efficiency over a period of wavelengths or over a range of wavelengths. And using their algorithms, they prove that the neural network could actually give you the conversion efficiency at different wavelength points as compared to an EM simulation solver. And this is the inspiration for this study. What if we're not going to use conversion efficiency, but the exact spectral responses like reflectance, transmittance, and absorbance, which are most of the time useful when we study metamaterials and metasurfaces, or even meta devices in general. So for this study, we will design the metagrating, we will simulate the devices using the FDTD, and we will also develop the simulation neural network architecture, train the SNN from our responses, from the responses in the FDTD simulation, and then we will characterize the SNN predictions. So this is the 3D model of the metagrating with a cylindrical element. We can replace a cylindrical element with other shapes. Then for the finite difference time domain, you have a 100-point frequency range from 1 gigahertz to 5 gigahertz. And then the element periodicity is at 1.5 cm. We made sure that it would be less than the operating wavelength, which is 6 centimeters at 5 gigahertz, which means sub-wavelength grating. Then the electromagnetic material properties, we set the permittivity, the permeability, and the conductivity to be 15, 1, and 0 respectively. And then we expect that the output of this FDTD would give us 100-point reflectance, transmittance, absorbance, and conservation test curves. And this is one single simulation, okay? And as you can see, this is how we get the responses using FDTD, using this EM solver. For the simulation neural network architecture, we use convolutional blocks and fully dense layers. Then the input layer would be 128 by 128 image. And then the output layer would be 100-point data. It means that it would resemble the frequency responses, 100 frequency points. And then we also individually, we have an individual SNN for each curve. One for reflectance curve, one for transmittance curve, and one for absorbance curve. Then this would be the hyperparameters in the data set. So for the training set, there would be 2,205 samples, which is 90% of the training set, the original number of samples, 2,450. Then we set aside 244 samples for the validation set, which is 10%. And then for the test set, it's around 100 samples, not belong to the initial 2,450 samples that was simulated. And then we also have a bulk test set. This is 1,329 samples that were simulated, not belong to the 2,450 to check the performance of the machine. Furthermore, we use a hardware. The hardware would be Core i7 20 CPUs, 12th generation Intel processor, and for the GPU we use GeForce RTX 360 Ti with 32 gigabytes of RAM. For the metrics, for us to understand the performance of the machine, we can look for the mean squared error. The closer to 0, the better. For the accuracy, if your accuracy is between 0.7 to 0.8, it's probably a good model. If it's between 0.8 to 0.9, it's an excellent model. But greater than that, your machine would be probably memorizing your training set. For the evaluation and prediction time, the faster the better. So we set it as less than 10 seconds. If the evaluation or prediction time is less than 10 seconds, the better, or much smaller than that. The average cosine similarity tells us the closeness of the data to itself. So if we have a cosine similarity between 0.99 and 0.9995, it's probably a good model. But greater than that, maybe your machine is memorizing already the training set. It's probably overfitting. For the results and discussion, I set the results to be in color so that you will not be looking at numbers only. So what would be the response, or what would be the results of the machine when we have your reflectance or transmittance or absorbance data set? As you can see, everything is green except for the reflectance data set, in which the accuracy of the label and prediction matching is at 0.46 or 46%. It means that it is relatively not good. But the other factors like average cosine similarity and mean squared error they are both good. So for us to understand the machine performance, we look at the plot of the label versus prediction in the reflectance dataset. And as you can see, they match. Based on this one, they really match. I mean, the plots are very close to each other. The green one would be the training label, and the dashed line would be the training prediction. It means that the machine predicts the device performance or the device responses, just like how your EM solvers could actually solve it in a very small period of time. And this is true also for transmittance and for the absorbance. How about for the validation set? Still, the reflectance data set shown very low accuracy, a little bit low accuracy. But if you look at the plots, the label and the prediction plots, they matches. Also for transmission and for the absorbance. For the test set is again another set that is outside 2450. The machine didn't see this data. And as you can see, the accuracy is 0.51, a very small, a small improvement over the validation and the training set. But everything is green, even for transmittance and absorbance. And for the machine, this is the result. For device 83, there is a little bit of mismatch, but the trend of the curve is similar. Also for device 67. For transmittance, everything looks nice. The label and prediction are a bit close. They are similar. And also for the absorbance, they are really fitting the curve. For the bulk test set, again, 1,329 samples. This is outside of the 2,450 training set. This is to further test the ability of the machine to predict results. And as you can see, for the reflectance dataset, there's a good fit. Okay? The test label and the test prediction are almost similar. Also for the transmission and for the absorbance. Then let's try a sample that is a little bit different from the dataset. And then I use this rectangle designed using Aseprite. It is a pixel art software. So this design is outside of our shape generating algorithm that was written in MATLAB. And then I imported it in SNN, tried to simulate it in the SNN, and then I also simulated it in FDTD and then compare the results. And these are the responses for this device. And it's promising since the result from the FDTD and from the SNN are somewhat close here. You can see the trend, okay? Although the exact values for each frequency were a little bit off. But for the absorbance, it's an utter failure. This is the needs improvement part of this algorithm. And this is where the SNN shines. The time requirement for the calculation or for the computation. Take note that the FDTD, to simulate all of the samples, it could take 8 to 21 hours. But for the SNN, it can just simulate it or give predictions on the responses for less than a second, 0.7 or 0.7 seconds, or even less than. It's a really significant difference in terms of the time or the amount of computational time that would take for the SNN to process predictions and for the FDTD to solve the entire Maxwell's equation. And it's actually normal since solving FDTD or using FDTD requires us to solve the partial differential equations of the Maxwell's equation, while the SNN will just try to understand the connection of the image to the label dataset, which is the spectral responses. For the conclusion, based on the metrics we used and the comparison of the label and prediction data, we conclude that the simulation neural network can be used to predict frequency responses of the device and can work hand in hand with usual EM solvers such as FDTD. Based on the execution time, SNN predicts responses at significantly much faster rate than FDTD, both with single and bulk samples. This is useful for decreasing time for simulating EM devices and can be valuable for rapid design, simulation, fabrication, and characterization of meta devices in general. And for some recommendation, we can increase the amount of training dataset to improve the training. We can also include more parameters, implement more robust CNN architecture, and implement generative adversarial networks to have an inverse design. So we'll have a complete look of the automation process. And thank you very much for listening and watching this presentation.